Добрий день, шановні студенти. У нас сьогодні гостьова лекція. Представник запрошується до доповіді пан Гарі. Павло, будь ласка, представте його.
Yes, so today we have a lecture that will be presented by one of the chief engineers, Harry Roberts, technical product manager for OPL and Sapphire. So, Harry, are you here?
Yes, I'm here.
Yeah, so welcome.
It's nice to meet you all today. Hopefully you'll get something out of this. And I think we're going to spend an hour, maybe some more time. It depends on if there's questions. And if I'm speaking too quickly, let me know and I'll try and slow down.
Okay.
Sure. So I'm Harry, as you said, technical product manager at Oasis Protocol Foundation and the Oasis network. I did a few months of like Russian and Ukrainian lessons, so I can read Cyrillic a little bit, but I can't understand much. But so let's get started today. So we're going to go over how to get started with Solidity. So I'm not sure how much experience you have with smart contracts or like blockchains, DeFi and tokens and DAOs, and or even if you've done auditing before, or if you've audited smart contracts. So I'm going to go over how to get started, the structure of Solidity contracts, then the manual auditing process. So I've worked in security before, and I've gone through lots of different audits, and there's a standard format that the industry kind of expects, so I'll walk you through that. Then the sort of vulnerabilities and categories. So Solidity is an odd language, but smart contracts and DeFi and DAOs, they all have their own sort of approaches to looking for vulnerabilities, and the different types of categories are all related to Solidity. Then I'll cover automated auditing tools. So these are like proof assistance, static analysis, stuff that can really help. And then I'll cover confidential EVM, which is what we do at Oasis. So it's EVM, but running inside a secure trusted enclave. So if you want to get started quickly, the best tool is Remix IDE. So if you want to follow along, it would be good to open up a browser and go to remix.ethereum.org. And it's just a web-based integrated development environment. So you can create smart contracts, you can compile them. It's got syntax highlighting, it's got lots of built-in tools. And this is really the easiest way to get started. So you can manage the files in the Remix IDE. So all of the smart contracts will be living in the contracts directory, and you can create new files, new folders, manage your stuff through there. And you can also download the entire directory that you've created. And all the metadata for the contract is going to be the artifacts directory. So what you'll be doing today, I'd hope, is compiling some smart contracts, maybe trying to build your own, and try to add some vulnerabilities in them, or fix some vulnerabilities, or just get used to the Solidity language. So in the IDE, you'll see that the compile errors come out as red. It'll provide all the compiling warnings for you. And when you press save, it will compile it. And you've got the sort of highlights there to indicate which lines they're on in the source editor, and I'll give you the syntax errors. But most importantly, if you have a contract that works and you're in the IDE and you want to start testing it, so after you've compiled it, you want to click on the deployment or the deployment tab. Then you can select the contract that you want to deploy and press the deploy button. And then when it's deployed, it'll get deployed to an address, and you can interact with the contract. So if you define a function here, I called it my method. It takes 2 arguments. You can input the arguments there. You press the call button, and it will give you the result. So it will handle all the typing, and it will give you passing of the arguments, and this is really, really easy to get started with. So yeah, I really wanted to do something a little bit interesting today. So if we can try to make a smart contract and try to add a vulnerability into the smart contract, I find that's really good for learning. And then if you want to share your contract as well and see, can other people find the vulnerability that you put in, or can you spot a vulnerability that they didn't know existed, and how crafty can you be? I think that's sort of an interesting game. And of course, if you want to put your name in there so we know who wrote it. But anyway, so smart contracts and Solidity. So smart contracts are ways of programming sort of programmable money on the blockchain. I'm not going to provide too much of a background there, but it's all written in Solidity. So if we look at this example where I want a tip jar, so somebody can send me money on the blockchain, and then every now and then I can withdraw that money to myself. So the structure of Solidity contracts, you have storage and memory. So the storage is like a key value database, and the owner property in there is in the storage. So when you when you deploy the contract, it will set the storage variable owner to whoever deployed the contract. So if you deploy it, then only you can do that. Then we have the withdraw method. So that requires that whoever's calling the withdraw function is the owner that created the contract. And if it is, then it will transfer the whole balance of the contract over to you. And there's lots and lots of features in Solidity that it's quite a well built out language. So over the years, you've got lots of different types. You've got libraries. You've got like utility functions. So I can add my own methods to a type by using the using structure, the using term. If you want to learn Solidity, there are lots of really, really good resources, but it's something that's going to take, like with everything else, writing Solidity, reading Solidity, exploring the documentation, and there is a lot of really, really good documentation. So if we look at the lifespan of a Solidity contract, so you've got your Solidity file, you run the compiler, which converts it into the contract bytecode. You then send the contract bytecode to to Ethereum or whichever blockchain you're using. That will save the bytecode in the storage, and it will give you the address of the contract. So every contract you deploy will have its own address. And of course, this costs gas. So you have to pay for all the storage you use. You have to pay to deploy contracts. And only the sort of public and external methods of the contract can be invoked. So by invoked, I mean you're sending a message to the blockchain along with enough gas money to pay for the execution, and that will send the message to the contract and execute the bytecode. So yeah, sending messages to the contract. Whenever you're executing a contract, there's a lot of context information. So this is read-only information that the contract has access to. So like message.data, that's all the data you send to the message to the contract, and that will be like the function arguments, like which method to call, and that's encoded in a way that's easy for Solidity to decode. Then you've got things like the message value. So that's how much ether you're sending to the contract, or how many tokens you're sending to the contract. Message.sender, which is who's calling the contract. And like transaction origin. So if you have multiple different contract calls, you can see who started the contract call initially, and then what was the most recent contract that's in that chain. But yeah, there's lots of documentation. I really encourage to search out Solidity tutorials. and the Solidity Lang docs are very comprehensive. So under the hood, Ethereum is a 256-bit stack machine. So that means each of the registers are 256-bit wide, rather than being 64 or 32 as you're normally used to. And it's a stack machine. So think of like the push and the duplicate and the swap and the pop operations. So when you're compiling your smart contracts behind the scenes, it's trying to convert that into the operations for the stack machine. You've got control flow, you've got the memory load and the memory store operations, and that's loading and saving a 256-bit word at a time. And then there's lots of other opcodes that are really specific to Ethereum that you're not going to see on anything else, like the self-destruct opcode that deletes the contract and deletes all the storage, which is an interesting one. And if you have a bit of background in C, I find that this is just a fairly simple way of explaining what's happening. So you've got the contract, which takes the message and the message length, along with a read-only context. And then every contract essentially has a switch statement to decide which method to invoke. So the first 4 bytes of the message data, that's going to be the hash of the function signature, the truncated hash of the function signature. And there's a great website, so etherscan.io. If you want to look at live contracts, live transactions, go to etherscan.io and go to transactions. And if you click on the address of any of the contracts, you can, a lot of people upload their source code, because if you're trying to be secure, you need to show people the code of your contract so they can trust it. And it's really interesting to explore these contracts there. And if you want to see like a live transaction and see the side effects, see the contracts that it calls, see what storage is modified, the tokenflow.live app is really, really useful. So I thought I'd start with those tools, because they're sort of everyone's go-to tools for figuring out what's happening on chain. So the Explorer, the Transaction Analyzer, that kind of thing. So yeah, let's try to move on to manual auditing. So essentially like performing analysis and writing reports. And as I said, there's a standard kind of format that everyone expects in the industry about auditing. So at the end of the day, if you're working as a security auditor, you'll be providing reports with your analysis. And generally, you start off with, if we're writing a simple report, just the specifics. So who, which is you, the project URL. This will probably be a GitHub project, or with a branch, or a zip file with a hash. So that says at a point in time, I'm auditing a very specific version of the software, so that we can see, oh, has it been changed since then, or is this the version that was audited? And we can figure out the difference between what's been audited and what developers have done since then. Like the general structure is, so like the overview, what does it do? A lot of the work involved in an audit is you're going to come across lots of different types of projects, and they all do their own thing. So like any kind of auditing work, you have to get an understanding of what it's doing first to be able to dig in and find out what's going on. And then I tend to look at like the high level structure, so the interactions between the different functions. What's the information flow? Then I try to like note what are the guards on each of the functions. So if I'm doing a quick analysis one by one of all the functions, I'll start mapping out all of this information. Then we move on to like the findings and analysis. So this is where in your report you'll be providing on each item what type of vulnerability it is, the criticality or how severe it is. And then depending on the project, you might want to get into the economics of it. So because it's on the blockchain, there's tokens, there's lots of interesting finance going on. Not all the vulnerabilities are in the code. So it's good to sort of sit back after you've got a really good understanding and try to look at how the money flows, or how the the governance token flows, or what shares are involved, who the people, to see if you can get a high level perspective. So I like to use a couple of tools to visualize the dependencies. Of course, I'll provide the slide deck with all the links to Alexandra afterwards. But generally, you get like a really useful high-level view of all of the different functions. So being able to very quickly say, oh, this function calls that function, or be able to see which functions modify this storage variable. And yeah, so like the criticality, each of the findings that we're trying to report to my client, for example, how critical is it? Right at the bottom, you've got like your opinion. So if people are paying for audits, they don't necessarily want your opinion because it's not, it's an opinion. It's not something that's broken. And right at the top, we've got everything's broken permanently. And of course, it's super, super critical. But then in between, you've got different varying degrees of how broken is it? Like how many different users does it affect? Is it likely? Or is it just not following the best practice? And then again, with every sort of, you might have like a really, really severe issue that is just it's a hunch, right? So it's an intuition that this is going to be broken. And those two together give you like a fairly good understanding of, I think this is, for example, really, really critical, but I can't prove it. It's theoretical. There are lots of different conditions that have to be met, but it's still worth conveying that information. So like an example of a finding report, you've got the severity critical, certainty mostly certain there. You need to list out so the functions involved, which contracts are involved, then the category, so the funds are at risk, along with the description. So this is usually a paragraph, maybe 2 paragraphs of your understanding of what does the function do, what's the cause of the vulnerability, and then what kind of mitigations can you put in place to the developer, the contract would have to add to prevent this from happening. And yeah, let's move on to vulnerabilities. So with all the different findings, you've got the general category, and there's actually like a smart contract vulnerability register there. So it's similar to the MITRE CWE, which is the common weakness enumeration. So each of the different types of vulnerabilities, or most common ones, are going to have some kind of code like SWC 127, which is an arbitrary jump with function type variable. And if you look at the SWC registry, you'll get a fairly good overview of what are the most common vulnerabilities that you encounter. But yeah, as I said, like not all the vulnerabilities are in the contract. So like today we're going to try and focus on Solidity, but in reality, the scope's a bit wider. So think of like all the developers, and they deploy the smart contract, and it's super secure, whatever, right? But the wallet that they've used to manage the contract is on their laptop, and it's full of malware, or someone has access to the Git repo and can publish new versions, or they can get into the website and replace the JavaScript on the site with like a hacked version. So a lot of people, they want to reduce the scope of the audit. So if you're looking just at the smart contract security, then that's usually really straightforward, but it forgets all of the other stuff that exists. And a lot of people don't want to pay attention to that, but it's worth thinking about. So I'm going to walk through a couple of just examples of different types of vulnerabilities. This is not an exhaustive list. I really do encourage go on Google. I'll share some links afterwards. You can dig in over the course of an evening and read the audit reports that other audit companies have written, because they all do a step-by-step breakdown of specifically the type of audit, of the flow of how the exploit happened. But if we start with something really, really simple, so I've got my internal withdraw function there. So it should be internal, and it's just a library function that shouldn't be accessible externally. But I've got the public modifier on that. So while in the withdraw function, I do the message sender check. I check if the whoever's calling the contract is the owner of the contract. But then if I want to invoke it directly, I can directly call the internal withdraw function, which is, you'd be surprised at how many times this happens, and surprised at how many audits that contracts go through where people just forget, and they only test the functions that they know that exists. And I think that the second sort of general topic, because it's important in the development of Solidity as a language, is until recently, integer overflows were prevalent everywhere. So sure, it's a 256-bit integer, but for example, if you're doing lots of calculations and you miss out checks for the overflows, then you could, for example, end up minting an infinite number of tokens, or sending lots more money than the contract thinks you should have, because you're able to overflow the 256-bit integer, and it wraps around again. And yeah, so one thing to note is in the newer versions of Solidity, it's got built-in overflow protection unless there's the unchecked wrapper. But in older versions, it didn't have the sort of built-in protection. So you'd see people using SafeMath, which was a common library that verifies that the operations you're doing don't overflow the size of the register. So if you see new code that's using SafeMath, the developer might not be great, because they're thinking like the old version of Solidity, but using a new compiler and not using all the features available. And the other problem that you have is that on Solidity, there's no floating point numbers. So there's no decimals, there's no rational numbers, and everything's done using integer math. So if you want to, say, for example, take 10% of something, you multiply by 100, then divide by 10, then divide by 100. Or, that's other ways of doing it. But something that's really common is people will modify some code. So a lot of contracts out there, they're not written from scratch. They're copied, or they're a fork of a project or just a copy. And one of the common things that people do is they'll try to change the fee structure. So they'll try to make it a little bit more expensive because they want more money. And they'll forget, when they're doing the calculation for calculating the fee, you end up with bugs like this, where the divisor's not correct on both sides. And this has happened a number of times, and it's led to sort of devastating attacks and exploits where basically all the money's just disappeared out of a contract because of 1 0 that's been left off something as someone has copied and pasted code. So I think the lesson to get from that is, if you do see a project that's a fork of another project, it's a really good idea to find the original project and look at the difference between the source codes for both of those. And then sort of digging a bit into the function call signatures and the mechanics of how methods are invoked in Solidity. Because you have a hash of the method signature that's truncated down to 4 bytes, you might see something in a contract that looks a bit odd because they share the same function signature. So if it's only 4 bytes, there's a big site of 4-byte signatures where you can go and find collisions. So if I have a contract that has a many message babbage as a function, that could end up causing interesting problems. But it's just it's one of these oddities that the more you dig into it, the stranger it gets. But it's worth knowing about. So if we think of smart contracts, so how can we make it get stuck forever, or how can we get a user's funds stuck? So if you're looking at an audit, you're trying to imagine all of the sort of malicious actions that you could take with the functions that are available to you. And one of those is taking control of the control flow of a function. So in this example, we're sending a payment to somebody. We're sending a deferred payment. So you can queue up a bunch of different payments. And then in the future, somebody can withdraw all the payments that are pending. Sorry. The problem is that if you can specify your own token there, then in the pull payments function, in this example, it will call your code. And there's no way of skipping across payments. So if you created a custom token there that whenever anybody tries to transfer any tokens, it just throws an exception, then anybody who calls the pull payments function, they'll get to your code, it'll throw an exception, and they'll never be able to receive their money again. So in this class of vulnerability, anywhere that you can put your own code into the loop somewhere, so you can take control of the control flow, it's an area that you should be looking for. I've got old slides here. Can you still see?
Yeah, we can.
Okay, sorry about that. Okay, so another oddity of Solidity is the delegate call function. So with delegate call, that lets you execute another contract, but in your with your own storage. So for example, I have a function here called delegate, and I use delegate call to call the target contract. And in my target contract, I set up the same variable in storage, and then in the function that's being called, I can set that to whatever I want. So rather than the storage being modified in the target contract, because you're doing a delegate call, it's essentially replacing, swapping the storage of the contract that you're being run with your own storage, so it can access all of your internal variables. Now you can imagine if you have a contract that can modify all of your internal variables, that can lead to some very bad things happening. And this, again, is a lot of people avoided delegate call because the possibility of accidentally ending up with an arbitrary contract that an attacker has written that can modify the contract's internal state, where the internal state would be all of the private information or all the information that you shouldn't have to modify. So like the balances, who the owner is, and there are a lot of situations where if you have the ability to change the storage values of a contract, these can be chained together in sometimes 2 or 3 long chains where you change the address of one contract. So while the vulnerability might not look that severe in terms of what you can and can't do directly, the 2 or 3 layers down, the sort of indirect effects of that could be devastating. And you have to look at the whole sort of interaction of the different contracts and what the impact would be of modifying that one storage variable in one place. So delegate call and upgradable contracts are very much linked together. So with an upgradable contract, the problem is that sometimes you don't want to deploy an immutable contract, and if there are any bugs, that means you can't fix them. So you create an upgradable contract, which is like a proxy that would be using delegate cool, and usually there's someone in charge of deciding when do we upgrade the contract. So if we find a bug or we want to add a new feature, you'd have the owner account or some kind of management account that would say, okay, let's swap out the code that's running behind this contract with the updated version. But again, one of the problems is who controls the keys. So I call the upgradable contract an admin backdoor, because while the contract could be completely secure and you trust the person who wrote the contract, what happens when they leave their laptop open at a conference and somebody steals the keys from their contract, right, or from their laptop? And if you have someone who can arbitrarily change the version of the contract and the code that's being executed, then that's a huge risk in itself. So it's a lot of people don't want to look at contract upgradability as being a problem because they think that they can be trusted and they're not going to act against your interests. So it's definitely worth raising any of these concerns you can think about in a report and getting them to address it directly. So can you reduce the amount of trust that you have with someone who's managing these contracts? And I think the last vulnerability that I want to go through is reentrancy. So again, with taking control of the code, the control flow and the code paths that are being executed, this can lead to some interesting problems. So in the example I'm going to show you, you have a contract that has a balance. So every user has a balance, and there's a withdraw function that will withdraw all of your balance. The problem is that when you perform a transfer and the destination of the transfer is a smart contract, then now you have control over the flow. So in this example, if I have a contract that starts to withdraw its balance, and then in my code, I then call the contract again and say, oh, withdraw my balance again. And if it hasn't updated the balance and subtracted the amount you've withdrawn until after it's called that, then you end up in a situation where you can withdraw much more money than you put in. So every time you call the withdraw balance function from within the withdraw balance function, then you'll still have the balance that was that you had before it was called. So an example of this is you've got your deposit function that increases your balance. Then you've got your withdraw function, and sure, you've got a check there that verifies that you've got a sufficient balance. But then we're sending that value to a contract, and then we're subtracting that. So in my contract call, if I then call withdraw again, that will re-enter the withdraw function with the same balance, and you'll be able to do that in a loop until all of the funds are exhausted. So next, I think I should move on to economic attacks. So yeah, so I think with smart contracts, like not everything is in the code is like a very important thing to remember. So with economic attacks, think of if I can somehow get hold of all of the shares of a company, I could liquidate the entire company, all of the assets, sell everything, take all the money, fire everyone, right? And in some jurisdictions, like these economic attacks are perfectly legal. Like in the US, you've got the mergers and acquisitions where this is a common pattern in business. And sometimes you can call it arbitrage. So I'm just getting something for less than it's worth. So if I can purchase all of the shares of a company for $1,000 and the company has $10,000 worth of assets, then the most straightforward thing to do is get all the shares, sell all the assets, and yeah, the problem is that in some jurisdictions this is a very legal gray area. So while like an economic attack might be possible, it might not be sort of ethical or moral. I'm sure your professor can talk to you about the ethics side of things. But of course, yeah, what happens if we set the value of a dollar to zero? What happens there? So yeah, the sort of common myths, yeah, so transaction ordering is random, or the miners are honest and you can trust them. So if you're looking at economic attacks, what if somebody has control over the order that your transactions are executed? So if you're trying to submit a transaction to the blockchain, you send it off, you pay for the gas. What if the miner who's ordering the transactions is working against you? And of course, yeah, nothing ever works as expected, and governance tokens and vows and DAOs and democracy doesn't always keep things safe. So I think one of the most interesting things about economic attacks is flash loans. So if you see an example of a contract, you go, oh, I would only be able to exploit that if I had $100 million. With flash loans, that's possible. So a flash loan is a way of borrowing money and then paying it back within the same transaction. So unlike with a loan, you borrow the money, they give the money to you, and then in the future, you pay it back to them. With flash loans, they're all on-chain in contracts, so the contract knows that it's received all the money back. And this means that sometimes you can have hundreds of millions of dollars at your disposal in a flash loan, from a flash loan source that you could use in an attack. And because it's a zero-sum game, imagine if after paying like the fees and the gas and the interest, you only make $1 from $100 million loan. And because it's a zero-sum game, that's still a profit. And it's especially a profit if you do this 1,000 times a day. So there are people out there using multi-million-dollar loans to attack, but also to make the markets function properly. So communicating price and so on. An example of this using Ether is you've got a function here, you've got the target, and you send the entire balance of your contract to the target contract. And then after the transfer, you just verify that you've still got the same balance or maybe a little bit more. So because you've when you send Ether to another contract, it executes the contract's code. In that contract, you can do whatever you want. You can do anything at all as long as you send the money back, or at least the same amount of money as you got before. And the other one is front running. So there's a great example of this I've seen, which is if you had a bug in your smart contract and you noticed it, but nobody else has noticed it. And the only way to prevent all the money from being stolen would be to exploit the bug yourself, to save everyone's money. So you create an exploit transaction, you send the transaction to the contract, and then somebody sees the transaction, and they front run you. So imagine if they pay just a little bit more gas, they get their transaction included before yours, and now they've got all the money. And because nobody knew an exploit existed until you told the world about it by broadcasting it on chain. And creating a front-running bot is really quite simple, but it's very important to think about. So if you wanted to make a front-running bot, you would just look at all of the transactions in the mempool, and then you simulate them, but coming from your account instead. And you do some quick checks, say, do I get more money than it costs in gas or fees or anything else? And a lot of this is automated. So there's front-running bots out there that are actively monitoring the mempool and are actively working against you. to get profit wherever they can. And yeah, so you can also abuse this. So if you don't have enough gas to pay for a transaction, but whoever makes a transaction is going to get some money back, then you can still send the transaction to the mempool, and these bots will go ahead and run them if it makes sense for them to. So if they'll make profit from it, then they'll go ahead and run that. The other problem is sandwich attacks. So if you think about transaction ordering, if you put a swap transaction, you want to, for example, swap $1,000 for Ethereum using one of these on-chain automated market makers, and you forget to set a price limit. So you just say, whatever the market gives me, whatever the exchange rate is, I want to get $1,000 worth of Ether. And of course, the attacker who's looking at the mempool sees your swap transaction, and they'll sell a lot of ETH first, which will reduce your buying power for Alice's dollars. And then after your transaction, they'll buy lots of ETH. So the price won't change, but in the middle where your transaction is, you'll get the worst possible imaginable exchange rate. So rather than getting $1,000 worth of ETH, you could end up getting $1 because you've got the transactions on either side of yours, which are manipulating exchange rates. And now this is all possible because using the automated market maker, the constant curve algorithm it uses is predictable. So the more you buy and the more you sell of an asset, that will increase or decrease the price. So if there's a lot of demand for Ethereum in the Ethereum dollar pair, then the value of Ethereum will go up in dollars. And this is used all over the Ethereum DeFi space because it's a fundamental component used to discover the price and to keep the markets functioning. So yeah, I've got some time left. Let's go through automated auditing. So there are a lot of tools out there. There's like a graveyard of open source projects over the years where people have tried to create the next best static analyzer for Solidity contracts. And there's lots of lazy auditors as well. So I call them audit mills, where you'll pay them, say, a few $1,000s, and they will run a tool, an audit tool on it, and they'll get the reports, and they haven't actually looked at the contract. So I think what I want to emphasize with like static analysis is there are tools. They're really, really useful. They can save you a lot of time and effort, but don't rely on them entirely. So if we start off with Slither, so that's essentially static analysis, and you create the vulnerability detectors that work on the syntax tree of the Solidity file. So the types of vulnerabilities you're going to get here are really quite basic. So it will pick up some function that does a transfer that doesn't have method protection or doesn't, I don't know, there's lots of like fairly basic types of vulnerabilities you can pick up, but because it's only looking at the syntax tree, it's not able to reason about your contract. So it's going to be like a search. It's a very simple sort of search there, but it'll pick up loads of really, really basic stuff. The second one I want to talk about, which is getting more into the sort of dynamic analysis, is Scribble. So Scribble is a specification language for you to describe invariants. So for example, in your contract, if you want to get towards formal verification of your contract, or you want to be very specific about how it should function in an ideal world or what it mustn't do, then you can start to annotate your contracts with these conditions. So in this example, say it will succeed if y is x plus 1. And of course, in reality, your properties are going to be much more complex. And the process of determining which properties you add to your contract, that it really depends on the contract itself. But the Scribble tool will take your annotations. It will then instrument your code with the annotations, which you can use either as a way of sort of being more resilient, or it can also help with the sort of dynamic execution plugins. So I need to get a drink. So the second one, so both of these tools are Scribble and Mithril by consensus, which is a very large company, very large company in the blockchain space. So Mithril does symbolic execution. So that's not just on the source code itself, but at the bytecode level. It has a full symbolic model of the EVM, and you can say things like, what are we doing in this example? Yeah, so you can verify if the state of the stack at any time during an execution path that it can find will have this condition. And rather than looking for sort of specific examples, it will try to find all of the possible inputs to a function that will end up with your state being true. So I've not given a particularly good example of that, but please do look at Mithril if you're interested in symbolic execution. It's a really great framework, and while it can take a bit of time to run and to get used to thinking in the sort of symbolic execution way, it will help you a lot. And so I think generally, if you look at Slither, Slither, Scribble, and Mithril, most of them won't catch all of the vulnerabilities. So they'll catch some really basic things, but they lack an understanding of what are the contracts supposed to do. And only as if you're auditing or pen testing a contract, it's up to you to define the conditions that are good, that are bad, that are vulnerable, and then to usually implement them in Scribble and Mithril to try and find either prove properties about individual functions. So, for example, proving that your balance will never be more than the amount of money you've put in is a good property to test. But yeah, combined together, they'll work really well. One thing to note about Mithril is that I've got the minus T1 argument on there, but Mithril can chain transactions together. So it can do a symbolic execution of calling every possible permutation of function after every other possible function. So if you want to look at a series of calls that are 3 or 4 levels deep, where you have multiple different transactions that are all interacting with the same contract one after another, you can do that with Mithril, and that can that can be really interesting. Right, I'll move on. So down the sort of symbolic execution rabbit hole, you have Manticore. So that's by Trail of Bits. So Manticore is a symbolic execution framework. Not only does it do EVM, but it also does x86 and quite a few other things. So this is used a lot in the reverse engineering community for exploit development to find the specific inputs to a function that will trigger a bug that you've spotted, where actually creating the condition, creating the inputs yourself is a really tedious, painstaking job. But if you can model the function and set up a set of constraints, then the symbolic analysis will provide you with the inputs to the function that will execute that. So yeah, you should. It also supports EVM. It's written by Trail of Bits, who are a very nice security company. And I think moving on a bit further, you've got like Z3 is a SMT solver and SAT solver. I use this quite often, where I don't necessarily need the full weight of Manticore or Mithril, or sometimes I just want to play around with the concept. And behind the scenes, Z3 is used by them. But if you want to use Z3 directly to find the inputs to a function that you can will exploit a specific condition, then you can model your model the function in Z3. The problem is it is converting from Solidity and the sort of programming it into the models, and that's a bit of a pain. And one of the problems you're going to run into is because EVM uses 256-bit integers, that's going to run very, very slowly sometimes. So if you're trying to search like a big space of what are all of the combinations of the different integers that will overflow, that will increase my balance, for example. So sometimes I will reduce that down to 8 bits or 16 bits and try to prove a hypothesis very quickly. And then I'll increase that to 256 bits and go and have lunch or something like that. And maybe in an hour, it will come back and it will say, yes, this is proven, here's the input, or it will say unsatisfied, I can't find a solution to this. And it's important that if you're using these symbolic execution tools, a lot of people will use a very low timeout. So they'll use maybe 5 seconds, 10 seconds, 20 seconds, and they go, oh, I ran a symbolic execution on these bytecodes, and it ran for 2 minutes. That means there mustn't be a vulnerability because it didn't find anything. Where in fact, if you removed the timer and went to bed and woke up the next morning, it would have found a vulnerability. It just would have taken a lot of time. Then if you want to go down into formal verification, there is the full sort of formal EVM semantics using KEVM. So similar to the symbolic execution with Mithril, Z3, Manticore, this allows you to model your contracts, the interaction between contracts, and start to prove formal properties. But the problem is with formal proofs, like all code, there can be bugs in your proofs. So you might miss conditions, you might prove some really basic stuff that doesn't actually encapsulate all of the things that could possibly go wrong. But at least with the K framework, you have like the RPC layer built modeled as well. So you can model your interaction with the Ethereum nodes that are executing your contracts, and you can use it to build more reliable systems so that you know that every possible state that your application will ever be in, you have accounted for this. And it's really tedious to work with though, but it's there and it's available. So I think I'm going to try to finish up with a little bit of an overview of a confidential EVM. So with EVM, everything's transparent. So if you look at Etherscan, for example, you can see all of the transactions. Not just that, you can see all of the inputs to the transactions. You can see all of the storage variables that are modified. But at Oasis, we're doing confidential EVM. So I call it the contracts with side channels, right? So it's executing in private. You've got private state, but you still have some information, such as how much gas did a contract call take? How long was the data? And you can infer some interesting things about that. But one of the examples that we use a lot is like randomness. So if I wanted to create a lottery contract, for example, where you have to deposit 1 ether to spin the lottery, and if you get 3 as a result, it will send back the entire balance of the contract. So you can do this, but the problem is that somebody can call your contract and see if it won, and if it didn't win, it can just revert the call and try it again. So it's kind of like having a time machine and trying to win the lottery, and you go through all the possible, you just try again until you eventually win it. So while you can have like random numbers on confidential EVM, you can store them in the contract. You have to be careful. So you have to usually end up with like a commit and reveal scheme. So if I have a commit to a spin where I put my deposit in there, because it's a confidential EVM and it has confidential storage, I can save the random number, and then later on you do the reveal. So you say, did that random number win the lottery? And that avoids this problem where you can revert the contract and try again. I think the second topic I want to bring up with confidential EVM is if you're trying to make like a private token, for example, and you want somebody else to be able to transfer money on your behalf, but you don't want anybody to see what your full balance is. So when you execute a transaction, you pay for gas, and some of the public information is how much gas did this contract execution cost. So that's why you have a side channel. So the gas usage can be a really, really good indicator of which code path did the contract take. So with a confidential EVM, you can't necessarily see the code path, but you can get an idea of how much gas it costs. So with this, for example, we've got two requirement statements, and the first one, it just checks, do I have enough balance to be able to perform this operation? The problem is that the two different code paths, they're going to have two different gas usages. So I can execute if you look at the number of bits in the 256-bit integer, I can start with a very, very large number, and then half that and half that and half that and half that until I get down to a very small number. And when the gas usage of the function changes, so it goes from one gas usage to another gas usage, that means that it's, in this case, it would have increased. So that means that the balance is sufficient for that. So I can then do that again, but in the forward direction. And using that, I can tap out using this sort of binary test for the exact balance of the contract. So if you wanted to fix that, you would have to change the order of your checks to verify that someone has authorization to spend before you check if they have the sufficient balance. So there's lots more interesting stuff with confidential EVM. I do encourage you to check out the website. But I think I've run out of slides, and I was wondering, does anybody have questions, or is there anything I didn't cover? Oops.
Yes, thank you, Harry, for your marvelous speech. So I have one question. Maybe I didn't get you right or miss some key information about smart contracts. So may you share us your knowledges about the way how to avoid smart contracts vulnerabilities and how to ensure their security?
So with avoiding smart contract vulnerabilities, I think one of the key problems is one is having a really good understanding of the Solidity language. So like with any language, the more that you get familiar with it and the edge cases with all of the different things. So all of the semantics of doing calls, how the contracts interact with each other, the more you understand Solidity, the easier it will be to, in your head, model the possible things that the contract can do. And then, of course, it's about restricting the contract to only doing things that you know it absolutely should do. So if you want to start with some kind of modeling, I find that straightforward. So saying, as a state machine, what is the contract doing? What are the users interacting with that? Can we break down at each step all of the possible states that it could have come from and all the possible states that it could go to, and then verify that the contract can only go in the direction that you want it. So I'm not sure if it's a very straightforward answer, but in terms of like making sure that it's secure, sometimes this can take a year or so and multiple different audits. And one of the weird things about smart contract security is that a lot of projects out there have been audited 2, 3, sometimes 4 times, and people miss the really, really, really basic things. And that's always annoying as an auditor when you look at something and you've gone through it and you're really sure that you've covered every possible angle, and then somebody points out something that that is so obvious, and that happens surprisingly frequently. The other problem is that if you're writing the code yourself, it's very difficult to audit your own code because you know how it works in your head. So this is really important to have somebody else work to audit your code. But then once you've given the code to someone else and they've audited it, then they now have an understanding of how they think you should work. So the next time they look at the code, they won't necessarily see the bugs if there was one introduced. A common thing you get is someone will make a smart contract, they will talk to an auditor, the auditor will point out a bug, and the auditor will suggest a way of fixing that bug. The developer will fix the bug using the recommendation, and that has fixed one bug but added another bug. So you then have to, if you've got an auditor who makes recommendations, you then have to audit the changes after they've been made to the contract so that you don't end up with more bugs being introduced. Does that kind of make sense?
So guys, some questions maybe? Don't be shy.
I'll say that I've got my email. If you do think of stuff, so you can send me an email. I'm more than happy to reply with links with whatever. I'll send the. Is it Alexandra who is organizing this? But I'll send her the slides, and I've also got some extra links that I'll send over and share with you guys.
I have one more question for you. Can you tell us some information about the Oasis network?
Sure. So the Oasis network, we have it's a layer 1, so we have our own consensus. At the consensus level, we have the Rose token, and we have multiple different paradigms. So the consensus layer is like a proof of stake network that ensures that the paradigms all agree on the same set of transactions, and transactions only go forwards and you don't reverse time, for example. And of the different paradigms we have 2 which are Ethereum compatible that can run Solidity, and then one that is not Ethereum compatible, but it runs WebAssembly, so you can compile Rust and run that. So we have 2 of these chains which are confidential. So the Cypher and Sapphire chains are both confidential, whereas the Emerald chain is just like Ethereum, it's a transparent chain. So I personally really like confidential chains because that means I can have contracts that have their own private state. And like an example of that is I can have a contract that generates a key pair, generates an Ethereum wallet, and I can use that to sign transactions. Or I can use 2-factor authentication like the TOTP codes. And I think we're reaching like the limits of what you can do with smart contracts on transparent chains because the contracts can't have their own private state. And that's like a real sort of hard limitation there. So while the Sapphire confidential EVM has only been out for about in production for 6 months or so, it is in mainnet. We are getting applications deployed, but we're still exploring the different uses for confidential EVM. So I think in the next like 6 months to a year, we're going to find lots more things you can do. And if you look at the like the evolution. So if you think of like Bitcoin to Ethereum, with Bitcoin, you started having programmable money. So you have in every single Bitcoin transaction opcodes for a bytecode that can do some very, very basic things. And then Ethereum took it to the next level, where instead of just a few opcodes, you've got a full Turing complete language, lots and lots more opcodes. You've got loops, you've got storage, you've got the ability for contracts to call each other, and that created a huge boom in innovation of people just trying to figure out what are the possibilities here. Then, like roughly, we had lots of different innovations in the mean, like lending, token systems, stable coins, and all of that happened on Ethereum. Then you started getting things like privacy, ZK snarks, and that's I'll get into ZK snarks some other time if you want, but we're reaching a point now where you can have privacy, but the contracts themselves can't have their own secrets. So while you can prove something, you can prove that you know something in private to a contract, and the contract doesn't know it. The contract can't be fully autonomous, so it can't operate the same way that web services do today. So if you think of like your normal web service, you've got a platform, you trust that whoever you're giving your data to, you trust that they're not going to view it and that customers can't view each other's data. But on Ethereum, everyone can see everyone's data, and that's it's a problem, right? So I think the direction we're going in is confidential EVM and being able to have contracts that can keep your data private, even from you or from other people.
Yes, thank you. I have one more question, but it's not about smart contracts. It's about cryptocurrency. What can you say about the current state of the cryptocurrency market? Did you monitor it?
So like the state of the market itself, I think we're coming up to an interesting couple of years. So think of the regulations that are coming in, and the past 5 years or so have been like a free party of lots of ups and downs, a lot of innovation. But it's getting more and more serious now. So I'm in the UK, and it's becoming difficult to create new currencies. It's being difficult to create new tokens or to play around with ideas, because it's not just magic internet money, it's like serious business. So the governments are getting involved, it's getting more and more regulated. And I think I just really hope that they don't shut it down too much. So for example, with privacy coins, I've been a big advocate for privacy for a long time, and we're getting more and more regulations that say you're not allowed to have privacy. And I think for me, just being able to have the same level of convenience and privacy as with Visa or when I pay with my card, I don't want everyone to be able to see my transactions. But the direction that the regulation is going in is we want to be able to see all your transactions. We don't want you to be able to deploy your own smart contracts, and we don't want you to do all this unregulated finance stuff. So I think they're trying to shut down the party, which is quite frustrating. So I think it's not going to happen straight away, and I'm not sure like who the winners or the losers are going to be. But if I were to say like Bitcoin versus Ethereum, I would probably go in the Ethereum direction, just because it's programmable and it's faster and can do much more. And that's assuming if in 5 years you're still allowed to transfer them off of an exchange and interact with the contracts directly.